Okay. So, in the last class we derived the optimal filter. It was x n as 0 being WSS, this is y n, desired response, this was the error. Okay. And our purpose is to minimize the error variance, and by that process we obtain the optimal filter, right. W opt, this is in general the filter coefficients. Again I write down our vectors and all that. W, these are all old stuff, I am just rewriting for our convenience. This is a filter coefficient vector or filter weight vector, input data vector. Y n we have seen is W transpose x n. Okay, we have already seen. Then R matrix is the input autocorrelation matrix. Because of WSS nature of x n, all the samples, it was independent of n, and the cross correlation vector again x n and all its samples and d n and all its samples, they are jointly stationary. Therefore, this vector, this x n vector, every term multiplied by d n and expected, that is a cross correlation, and they are all independent of n. So, this vector is a cross correlation vector p. Then what we obtained is this epsilon square was expected value of E square n, that is output error power expected, average power of the output error, and that we tried to minimize. Okay. How? Because E n was d n minus this w y n is W transpose x n. If you really expand W transpose x n as nothing but W 0 current sample plus W 1, it is a convolution x n minus 1 dot 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 W n minus 1 x n minus capital N plus 1. And then if you square up E square n, so square up, then expected. So, there will be from this side when you square it up, there will be x square n, its expected value will give the variance, but there will be W 0 square, there will be W 1 square. Okay. Variance or correlations are given to us. So, x n into x n minus 1, there will be a term W 0 W 1, corresponding product here will be x n into x n minus 1, expected value of that, this correlation with gap 1, which is given to us. All correlation values as may be necessary are given, but in terms of W 0 W 1, you see there will be a W 0 square term, W 1 square term, dot dot W n minus 1 square term, W 0 W 1, W 0 W 2, W 1 W 2, all second order. Then d square n, and then again d n with, when you multiply d n with this term, W 0 will remain as it is. There is no W coming from this side. So, they are first order terms W 0, W 1, W 2, just x n multiplied by d n or x n minus 1 multiplied by d n and so and so. But here when I square it up this part, okay, W transpose x n, which is this, then I get second order terms. So, overall it is a second order function, and we actually worked it out. It was variance of this d n minus twice W transpose p. This is the first order term, okay, W 0, P 0, W 1, P 1 like that, which is coming basically by applying from the product between d n on one side and the terms on this side. So, d n into x n, d n into x n minus 1, they give the elements of p vector, but we all have only W 0, W 1, W n, not W 0 square, W 1 square, etc. This is that linear term, first order term. And from here, the other one was W transpose R W. This was having the second order terms. Like if you square it up, whatever you get, that is what you will get here. So, in general, this was a compact expression in terms of vector and matrices. This is just elaborate expression, but in either case, this variance is a second order function of the filter weights, because it has got second order terms like W0 square, W1 square, W2 square, W0, W1, W1, W2 and dot dot dot, also first order terms W0, W1, W2 all multiplied by some scalars which are correlations or variances. Okay. Then I said any second order function will have a unique minima or maxima, in this case minima. So, I just take the partial derivative with respect to each weight of this equate to 0. Okay. So, I get capital N first order equations, because second order stuff when derived, okay, with respect to these terms, okay, W0, W1 etc., you get first order. So, you get capital N number of first order equations involving n unknowns, these weights, solve them, you get this W opt, right. Now, here the problem is, that is W opt was R inverse P. Now, here problem is you need to know R and P, and we are assuming R, there is input autocorrelation matrix, and P, there is a cross correlation vector between x n and d n. P is x n d n, sorry, I missed out. P they are fixed, they are not changing, they are fixed, all right. But in practice it does not happen like that often. Input both x n and d n, their properties change, statistical properties change, because the circumstances, the forces which generate them, circumstances which generate them, they change from time to time. As a result, R changes from time to time, P changes from time to time. So, if you design the filter with one R inverse P for certain R and certain P, that is an optimal filter, it will work fine for a while. But if R matrix changes and the P vector changes due to environmental changes outside, circumstance changes outside, then the filter that we are using now will no longer be the optimal filter for the new input statistics. But you cannot go on changing, you cannot go on disbanding the circuit manually and then again recalculate and again reconstruct the circuit, again use it for a while, that is impractical, that you cannot do. So, we look for a filter which will learn from the input, incoming input, learn the changes in R and will adjust the filter coefficients iteratively, that is clock cycle after clock cycle iteratively. So, that if R changes and P changes, it will take these coefficients to the new W opt, which is new R inverse new P, okay, and it will go on. Such a filter will be called adaptive filter. So, there will be an adaptation process by which the filter coefficients will be adapted clock after clock or index after index, nth index to n plus 1th index to n plus 2th index, that will be changed by an adaptation algorithm. That is what is needed, and I have to go there from here. But there is an intermediate step called gradient descent step, gradient descent. Okay. From here we have to go to the gradient descent approach, from there I will be able to arrive at the adaptive filter. And again I have taken all real case here. Fine. To go to the gradient descent step, from here I have one particular way of explaining, and that is this, that suppose you know R, you know P, but you do not know how to calculate R inverse. It is a big matrix, you do not know. So, you tell me that look, I do not know how to calculate R inverse, so I cannot calculate W opt, though it is offline calculation only. Can you suggest me some other method, maybe an iterative method, where I run iteration after iteration after iteration, but no inverse of R is required, and it takes me to W opt in the end? I say yes, and that is this step. Now, that to go to that step, we first note that if I plot this epsilon square as a function of all these weights, so it will be a quadratic surface, quadratic function, because it will have that will have a unique minima. That will have a unique minima. It is a quadratic function. Okay. Let me show this by taking an example of just one filter coefficient, not W0, W and all that. Suppose only W, x n. So, y n, which is just W times x n, as an example. So, E n is d n minus W x n, you square it up, d n square, W square x n square, expected value will be R 0 0, R x x 0. So, there will be a W square R x x 0 0, there will be d n square expected, there is sigma d square, and there will be a minus twice expected value of W x n d n. which is a cross correlation. So, it is a second order thing, a sigma d square minus twice w into a scalar plus w square into a scalar. So, second order. Any second order function, now if I want to plot it, I have taken only one coefficient, because then it becomes easy to plot and explain. So, this epsilon square in this case is as before. So, epsilon square, it is a quadratic function of w, and as I know, any quadratic function will have a unique minima or maxima, in this case minima. So, it will have a minima maybe at w opt, and this is my w axis, and it will have minimum value this much. And moreover, if I go along on both sides, it will only go up, up, up. It can never come down like this, or come, because when I differentiate it with respect to w, I get and equate to 0, I get only a single solution, not multiple solutions. So, gradient, that is derivative, will be 0 only at one point. So, if it is that point where it is a minima, it can have a unique minima, only one minima. It cannot have multiple minima or multiple maxima. That is, if I derive with respect to w, I get a first order equation. First order equation has one solution. Okay. Like here, E square n, if you plot it, E n is d n minus w x n, as I told you, d n minus w x n you put here and square up an expected value. E of d square n will have sigma d square. Maybe I use this pen. Minus 2 E of w x n d n. So, w is outside and x n d n is a cross correlation, you can call it p, small p, just one coefficient, so I am calling it p, and w, and then w square x n square, w square x n square expected value will be r 0 or x x 0. So, it will be w square or x x 0, right. So, it is second order stuff, you see. So, if I derive it, I will get a first order equation, and when I make that equal to 0 and find out the minima or maxima, I will get a unique minima, only one solution. So, if that is the unique minima, I cannot have multiple, okay, which means this function can only go up, 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 it can never bend, that is most important. Okay, whether it is a function of just one weight or have got all the weights. It is a quadratic surface, in this case a quadratic curve, in general a quadratic surface. Now, suppose I am running an iteration, okay, and at ith iterate I have got a coefficient w I, all right, ith iteration. So, it can be either to the right of this or to the left of this. I am not assuming this is equal to this, because then I am already at the solution. So, that is a trivial case. So, let us suppose it is on this side. At ith step of iteration, I got some value of this, some estimate of this w opt, that is w equal to w I, which is in this case is to the right of this, could have been to the left. As an example, I am taking on the right. What I do then, I find out at w I this value epsilon square and see the gradient at that point. And from this, I subtract, I will explain, I subtract, I first take the derivative. In this case, I can write in terms of d, because only one variable. So, d dw, there is a derivative, and that I evaluate at w equal to w, that point, w I, and I take something proportional to this. There is a proportionality constant mu times, that is a quantity which is proportional to the gradient. This is a gradient proportional, this is a proportionality constant, it is called mu. Instead of mu, I take it mu by 2, because then a 2 will come after some time, and that will cancel with this. Mu by 2 is the proportionality constant. This is what I do, I subtract it from the current iterate, and whatever is the result, that I take to be the value in the next iteration. What I am doing here actually, you see, if I am on the right side of w opt, then gradient is positive. So, this is positive and mu is positive of course. So, from this I am subtracting something positive. That means, from here I am not going to the right side, I am subtracting something positive, means I am going in this direction, which is the correct direction to approach W opt. Okay. So, maybe I cross this, I subtract something, it takes me here. Now, if I am here, gradient is negative. So, negative, negative, positive. So, I add something to this iterate. So, maybe it takes me there, and like this, like this, like this, finally it will converge here. Okay. This is the method. This mu is very important, mu is called step size. Remember one thing, I am taking this to be positive or negative. If it is positive, I am subtracting, but the amount by which I am subtracting, this whole quantity also depends on the magnitude of this. If I am here where the gradient is very steep, value of magnitude of the gradient is high. So, this quantity is called the update part, update part or increment or decrement part, that itself will have large magnitude. So, that is why I jumped here. But if I was here, then the gradient may be positive, but magnitude of the gradient is small. So, this whole thing will be small. So, I will be just going by a small amount. So, when I am further away from on either side from the W opt, this scheme will take me, will go by a big jump, but when I am around this, jumps will be small, but it will go like this. Okay. And this update part also proportional to mu. If mu make very small, even if this is large, this whole quantity will be small. So, from Wi you will be going back by small margin, there small margin, small, small, further small, small, and like that. So, it will be taking lot of time to converge. On the other hand, if you now become greedy, you say no, let me increase mu, then of course, it will be, it can be like this, it goes here, then here, then here, then here, then here, then like this. Finally, you say that no, I am still greedy, I have to make it still further. So, let us increase mu further. Then it may so happen, you go here, you subtract and go here. But next time, then from here you go here, so it will be like this. So, you will be oscillating between the two, you will never come down. So, that is the point of divergence. You cannot cross mu, take mu to that level, so that this phenomenon occurs. Then you will never come down and converge here. If I still become greedier, then from here I will not go here, I will go further to the left. So, I will go up to this, and from here I will go like this, then like this, I will go up, it will diverge. This shows it has an upper limit for convergence. All right. Physically it is clear, mathematically it can be worked out, but as I told you, steepest descent is not my cup of tea here, because I will be, this is just an intermediate stage to take me to adaptive filter. Okay. Descent, because I am subtracting. So, from top I am coming down, so descent, and steepest because actually I am going down along the direction of the gradient. If it is a function of many variables, suppose it is a function of two filter weights W0, W1, then this plot will be a bowl kind of thing. So, at any point I take a gradient both with respect to W0, W1, and I carry out the subtraction. So, basically I go down along the direction of gradient, that is the steepest gradient. Anyway, this was for one coefficient, right. Suppose I extend it to multiple. There is now I got W0, W1 dot 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 W n minus 1. In this case, for example, if it is only W0, W1, this whole curve this will be a 3-dimensional plot. This is W0 axis, this is W1 axis, and this is your epsilon square. In that case, your plot will be like this. It is a bowl, cup shaped. Okay. So, here at any point you go down by subtracting, because at this point I have both, this point is a function of both W0 and W1. This point I can have gradient both with respect to W0 also, W1 also. If both gradients are positive, I come down. Okay, like here, if the both gradients are positive, I come down. Okay, if one gradient is positive, one gradient is negative, in one case I come down, another case I go up, and like that. Okay. So, I follow the gradient, and that, but by that I am coming down and down vertically in the vertical direction. So, that is why it is descent. So, in general, philosophy is same. So, I can extend it to now not just one filter coefficient, all the coefficients together. W0 I plus 1 is W0 I minus mu by 2, this derivative with respect to W0, not others, W0 gradient with respect to, and it will be partial derivative now, del epsilon square del W0 at that point where overall W is Wi. Okay, that is, this is W0 I, this is W1 I, this is Wn minus an I, at ith iterated their values. So, W standing there, there I find the gradient, subtract, that is for W0. In general, for any Wk, it will be minus mu by 2 partial derivative now, because it is a function of so many, not one. So, Wk derivative with this to Wk, I go in the negative, I mean I subtract this derivative from Wki, but this has to be evaluated when W is standing at Wi, that is W0 I, W1 I, dot dot dot, Wn minus 1 I, because epsilon square is a function of all the weights. So, this derivative also will be a function of all the weights. I am deriving with respect to Wk, but after derivative still it may be a function of all the weights. So, there all these W's have to be put in, W0 I, W1 I, and all that. And now, if I stack all these updates on the left hand side, on the right hand side, then it will be one vector with W0 I plus 1, W1 I plus 1, W2 I plus 1, dot dot dot, which is nothing but in the vector notation W I plus 1, and that is your Wi minus mu by 2, and now I have got del notation, del epsilon square del W0, del epsilon square del W1, they are stacked. So, it is del W. So, that is a stack of the derivatives evaluated at, this is the steepest descent algorithm. This derivative we have already found out in the previous class. This derivative, and that was what? Del W epsilon square, it was equal to twice RW, if I recall correctly, minus twice P. You can check, this is what we derived. All right. So, you can put it here, this 2 is common, 2 and 2 cancels, take minus out. So, you have W I plus mu P minus R W, and put W equal to W I. So, this is the equation. If R and P are known, there is no inverse of R required here. So, that is what you wanted, no inversion of R, fine. So, go on from Wi to Wi plus 1, calculate like this, then again like that, Wi plus 2, I plus 3 like that, and if mu is chosen correctly within the limit, this diagram itself shows that it will go like this, like this, like this, finally will hit the optimal vector, optimal weight exactly. It is absolute convergence, exact convergence, this method of steepest descent. But still you see, I have that problem, this also depends on knowledge of exact R, exact P, exact R, exact P. Okay. So, that is what I want to avoid. So, what I will do, let us assume that I am carrying out the iteration in real time. That is, we are carrying out the iteration by looking at a clock. Clock means the clock waveform, not your wristwatch, clock waveform. So, nth iteration or maybe ith iteration to in ith clock. So, I replace I by n, because normally you know n is the letter that is used typically to indicate a clock, nth clock or nth index, all that, not ith index. So, at nth clock we carry out nth iteration. I prefer n rather than I, so I replace by n. So, that whole iteration you are looking at the waveform at nth clock, you are doing the nth iteration, that is from W n you are going to W n plus 1. Then at n plus 1th clock you are doing from W n plus 1 to W n plus 2 and so on and so forth. All right. So, we are running in real time. Suppose I do that, and also we know R, this is E now. Suppose in real life you want to estimate this, what you should do? You should take one sample vector full with all numerical data, I repeat numerical data, random numerical data, take this matrix. So, you get a matrix of data. Then take another case, maybe x n minus 1 vector, they are vector transpose, second some data here is transpose another matrix and dot 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 dot, maybe you take many cases n minus L and average them. How many cases I have? L plus 1, 0, 1, 2 up to L plus 1. So, this will be a good estimate of R, isn't it? You take one data vector multiplied by its transpose, another data vector multiplied by transpose, this thing. So, you are taking case by case, basically it is called sample averaging. You are taking samples of x n, obtaining one instance of this matrix, again samples of x n minus 1, another instance of this matrix, x n transpose this matrix. Okay. And like that, and then you average. More the number of such cases, better is the average. But suppose to start with, I am not bothered about how good the estimate is. Actually, it will be a very good estimate, we will see later. But I just say that I will take only one case, L equal to 0, only one case. So, it will be a bad, so called quote unquote bad estimate, but suppose I do not mind, I can still show convergence and all that. So, in that case we replace R by just one instance only, just one sample vector into its transpose, that is all. It is not a good estimate because I am not doing averaging, but suppose I do that. Similarly, P vector approximately, now what is P vector? E of x n d n, okay, which means approximately you should have x n one sample data vector, random data vector times random d n, then x n minus 1 vector into d n minus 1, so another random data vector in d n minus 1 and dot 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 x n minus L d n minus L. Okay. But again I do not mind having a so called quote unquote bad estimate, I will just keep only one. So, P I will replace by just x n d n. In that case, let us see what happens to that. this one. I goes to n, so it will be W n plus 1. At nth clock, it will be W n plus mu. P I will replace by what estimate I got, R replaced by what estimate got, and W n. Okay. So, I will get W n plus 1 as W n plus mu P minus R W n. P is x n d n, x n vector into d n minus R W n, R is x n x transpose n, column vector, row vector, and W I it was, now it is W n, because I is replaced by n. Now, I take x n vector here also I can take it common. So, let x n come out. So, I am left with d n here, so x n into d n and x n into x transpose n W n. Now, suppose I constructed the filter, this filter coefficients at the nth clock are not just W 0, because they are changing from clock to clock, okay, iteratively, because I am moving them from W n to W n plus 1. So, at nth clock I have got W 0 n to W n minus n. Okay. Then, and you define W n okay, at nth clock I have got the filter coefficient vectors, nth iteration, nth iterate or nth clock, that is why n is coming, okay, because I am changing from n to n plus 1. So, in the very next clock their values will change, that is why I had to bring in the n here to show their dependence on n, and this is W n, this is your x n vector. So, output y n you know will be W transpose n now, this vector transpose W transpose n x n, but that is also same as x transpose n W n. You know that if I give you two vectors, column vectors A and B, A transpose B is same as B transpose A, isn't it? A 1 B 1 plus A 2 B 2 plus A 3 B 3 like that, or B 1 A 1 plus B 2 A 2 plus. So, that is what I have here. So, this is y n, and d n minus y n is the error E n. So, that is that equation which I will expand in the next class. This is a famous adaptation equation called LMS. So, I rewrite, I will just take one more minute. So, this is my equation, update or adaptive filter equation. At nth clock I got some filter weights, I change it in the next clock to this by what? By adding an extra term called update term mu into x n E n, where E n is d n minus y n, this desired response minus the filter output, and filter output it uses the filters here, coefficients here, and the input vector. You can write this way, and this will continue for n equal to maybe 0 to end. N equal to, let me write this somewhere else, because there is no space here. So, for n equal to 0 to anything, maybe final, some index of your choice, call it final. You do this end. Only thing is, at n equal to 0, W 1, it requires W 0. So, W 0 is an initial value, that you have to provide. Any initial value will work. Normally, we prefer W0 as 0 vector. This is called least mean square algorithm, LMS, one of the two most popular famous adaptive filter algorithm. It will also converge, but remember R matrix was not giving the proper value, P vector was not giving the proper value, just some approximate wild estimates were given, x n into x transpose n and x n into d n. So, for that you pay some price. Here the convergence, suppose you take a particular filter coefficient W k n and this is the W k opt. This will not converge on this absolutely, unlike the previous case of steepest descent. What it will do, this is also now random, because you see from nth index when I go to n plus 1th, I am adding an update term which are data dependent and data is random, which makes it random. So, it will be randomly fluctuating. So, mean of fluctuation, average may be here, after some time average might be here, then maybe here, like that, but finally, it will be oscillating, randomly fluctuating around the W k opt. This is what we can ensure. Okay, it will not converge on this absolutely. So, what we will observe, what we will say, all the weights, if you take the mean, that is the average, and go in the steady state, means for large n, that will go to optimal. It is only for kth case, here all the cases put together. So, as n tends to infinity, expected value of the fluctuations of each, that is the average was here, later here, but in the end average of the fluctuation will coincide with the corresponding optimal. So, it will converge in mean. That is a problem of LMS, it is not converging absolutely. Now, you can ask me, fine, it is converging in mean, but if still the range of fluctuation is large, then what will you do? Sometimes jumping here, sometimes jumping here. Then we show, and we will not be able to maybe show in this course the theory, but I will tell you there is a way to keep this fluctuation range small by again mu. If you choose mu less, then this also will be less. So, first LMS algorithm converges in mean, and then by appropriate choice of mu, you can keep the range of fluctuation very small around the optimal one. So, that is fine with us. So, this is the famous algorithm LMS. We will prove its convergence also maybe in the next class. Thank you very much.